Okay.
Let's begin.
I said A, B, not
So, last time we covered a topic called improper integrals. So it was when one of the assumptions of the fundamental, one or several assumptions from the fundamental theorem of calculus did not hold. That means you had an integral from A to B of f of x such that what were the three things that we looked for to make sure it was improper? Yeah?
B was infinity.
B is infinity, and or
A is negative infinity.
A is negative infinity, and or what? F is discontinuous.
But I'm pushing it though.
Try not to many points in AD. Right? So, the fundamental theorem of calculus could not deal with these situations. And so we had to come up with a whole new idea of the improper integral, where we use limits to approach these situations and somehow get a handle on the integral that way. And it turns out that a lot of times you can have a finite, meaningful answer to this, which has a lot of applications, which we're not going to see them now, but in future classes you realize that there are a lot of applications for improper integrals. Then we ended the session with talking about the comparison theorems. So there is the direct comparison theorem. So this is just, we already have this, so you don't have to copy this up. So there was the direct comparison, right, which basically said if you know that 0 is less than f less than g, and then it implies that if g converges, so does f. So there's the integral of f. And if the integral of f diverges, so does g. Integral of g. And we also have the limit comparison test. So that was if we look at the limit as x approaches infinity of f divided by g, that was L, where L is finite, positive. Then you can make the conclusion from that that this and that both converge or both diverge. Right, so those were the comparison theorems. And we didn't really do any examples on that one. We just stated that. So that's what these guys are about. More examples of us using the comparison theorems. Because sometimes directly actually computing the integral to check whether it converges is not an option. So what we're going to do is to determine the convergence of these guys without actually computing them. And that's the power of the comparison theorems. Just knowing that there is a meaningful answer as opposed to actually finding the answer. So that's what we're going to do. So the comparison theorem can actually help us get a handle on all of these. And on all of these, the integration would actually be either messy, very messy, or impossible. So we're not going to do the integration. I just want to make sure you guys are seeing how we want to apply the comparison theorems in a situation that they're needed. So, give me some ideas. 0 to infinity, x over x cubed plus 1. Let's just jump in. Ideas.
Break it up?
Break it up how?
Oh wait, never mind. It's already showing.
That one is b infinity, and x is minus 1.
X to minus 1. Coming in? Coming in? What? I missed what you said.
The endpoint is b infinity, equal infinity,
Right.
and the x is minus 1.
Right. X is minus 1 is not an issue though, because it starts at 0 going up. So x equals minus 1 is not infinity. So yes, the only bad point here is the actual infinite point. Okay, so this is improper because of that. Now, how do we deal with that? Yes.
Integral 0 to a.
We don't want to directly compute the integral. That's the whole point. We want to actually try the comparison theorem. Which means you should be thinking of something to compare this to. Yeah?
Oh, can you compare to 1 over x to the third plus 1?
Do you know about 1 over x to the third plus 1? Do you know what's going to happen to this? Yep.
You can compare it to like 1 over x to the second. But first I split it because you're thinking of the integral from a to the constant to infinity, a constant greater than 0 of 1 over x to the p, and if p is greater than...
Oh, well, specifically, 1 was what's used in that theorem. So we know that the integral of 1 over x to the p dx converges if and only if your p is larger than 1. And so you look at this and you're like, well, if I kind of forget about that 1, it'll kind of look like 1 over x squared. The problem is, the theorem says we need to start at 1.
So I split it. So like the integral from 0 to 1 of x over x plus 1 plus the integral from 1 to infinity of yes. So when you're approaching infinity, it's essentially going to follow the highest term of each of the numerator and denominator. So x over x cubed, which can simplify to 1 over x squared. So I would
Yeah, but how would you
compare
apply
it-
the comparison?
I would compare it to the integral from 1 to infinity of 1 over x squared.
Okay, so we're going to compare this guy to 1 over x squared. And we're going to compare, well, this guy can just be the same, right? Because he's just going to be a constant. Right? That's going to be some integral that you'll be able to find the area of, right? Because from 0 to 1, it's fully defined on this interval. So this is just going to be some constant. So I don't have to worry about that. That converges. Now, how does this guy compare to that guy?
Well, you know that one converges.
Yes.
So I would see, in order to apply the comparison theorem, if it converges, if the function you know converges, the other function has to be smaller than that function.
Okay,
So
that's it.
I would set up like an inequality. X over x cubed plus 1 has to be less than 1 over x squared, and like solve and see if it's true. If it's not true, then that means that the direct comparison theorem doesn't work.
Is it true that this one is? How would you know if that's true or not? Yeah.
Well, I mean, you essentially like subtracted 1 from the denominator,
Right.
the second one,
So-
and so that would make it bigger.
Right, so to go from this one to that one, I made the denominator smaller. And that means this guy is actually larger, right? So the inequality does go this way. Right? You don't really have to worry about the calculations. One way to know how to make a fraction bigger is to make the denominator smaller. And that's in fact what you did. If you subtract 1 from the denominator, you made it smaller. You would end up with a bigger fraction. And so now we know that this converges. So this is just a number. This converges by theorem. Which means this whole thing is a number, and it's larger than that whole thing. So this means, so this is I. I converges by the comparison theorem. Specifically the direct comparison theorem. I just found something that's larger than it that converges. So it's a different kind of intuition that we're playing with now. I don't really care about computing the integral itself. I want to find some other integral that's easier to deal with, that, for one, I know about it, and for second, it actually obeys the inequalities in the direction that I want it to obey them in. So I know about this because it's just a 1 over x to the p integral, and I know that converges if p is greater than 1, here p is 2, so that converges. Now, knowing that that is bigger than this will tell me that this will converge. And of course, these are both, which is equally important, greater than or equal to 0. So pretty much I had my 0 is less than or equal to f, less than or equal to g. Specifically, this guy is going to be less than or equal to that guy. And so this means that this guy is going to be less than or equal to that guy. And I know this one converges. So it forces this one to converge by comparison. Now, again, you have to know the theorems very specifically. You have to memorize the rules very specifically. I probably should have quizzed you on that theorem, by the way, now that I think about it. There has to be a 1 down here for you to apply that rule. So the fact that there was a 0 down here, that is a problem, but you could just break the integral into 2 parts. That's just going to be some number. You can apply the comparison theorem on the second integral. So, yeah, the first one converges by direct comparison. So, now that we've made it through a problem, we actually covered a lot of nuances in this problem actually. Let's look at the second one. Let's see if we can actually get to the answer with that one quicker. This one is very hard. If it were complex analysis, we could compute that exactly, but in Calc 2 we can't. We don't know enough to actually compute that integral directly. So a comparison theorem really is the only game in town here to know if it converges. Right? What are you thinking? What's making this integral difficult, do you think?
0.
The 0?
No, like to like break it up.
No, I mean the integral itself. What's making it difficult? The numerator, the cosine squared, right? It's very weird. Would you know how to deal with this integral?
Yes.
Yeah.
Yeah, we have a formula for that integral. How does this one compare to that one? Look at this, like 0 to infinity. How does this compare to that? So actually, let's focus on this one for a little bit. What would this actually be?
Okay. RJ.
Over
well.
2.
So limit as n approaches infinity from 0 to n of 1 over x squared plus 1. X, this would be the limit as n approaches infinity of, oh, that's tan inverse. That was hard too. We actually did this one last time. So I know that integral converges. So that's an integral that I actually know about. 0 to infinity of 1 over 1 plus x squared. We know that actually it's pi over 2. Okay, so how do we use that to help us here? Because that's kind of the guy we want to use. Yeah,
Isn't the right one bigger than the left?
how do you know?
Because the cosine squared x is like, no matter what it is less than or equal to 1.
Okay,
So, and considering that the numerator for the right one is 1, you could say that it's greater than or equal to the left. I can't
okay.
put it
So we know that cosine squared x is less than or equal to 1.
Yeah.
Is that good enough to apply the theorems that we need? Because yes, that does mean that if this is, because 1 plus x squared is a positive number, I can divide both sides. And that inequality would still be true. Yeah, that's actually true. So are we good? Huh?
So can't you set up the right hand as like your g of x, and then since that converges, the left also converges?
There's something missing.
Positive 0.
Hmm?
Needs to be greater than or equal to 0.
Needs to be greater than or equal to 0. That's actually an important part of the theorem, believe it or not. Is cosine squared greater than or equal to 0?
Yes.
Yeah, it's a square, right? So we have that, which means we have that. This is actually an important part, don't ignore that. There are a lot of problems that you'll get into trouble for not having the 0 on the other hand. Right? So when you're looking at the theorem, the direct comparison theorem, it says 0 is less than or equal to f, which is less than or equal to g. You have to have all inequalities in play, or else the theorem might not work, because you can have things diverging to negative infinity, which destroys the theorem. You don't want that to happen, right? So these guys have to be positive. Now cosine itself is between -1 and 1, but when I square it, it's now between 0 and 1 because it's a square. So I have, this is going to be true. This is just, by definition of cosine, that's going to be true. Now I can build up to that function by dividing both sides by that. So that's like my f and my g. It also implies that if I were to take the integral from 0 to infinity of this guy, it's going to be less than the integral from 0 to infinity of that guy. And this equals that. So this guy, 1/1 plus x squared dx, converges. Which means the original converges, 0 to infinity of cosine squared of x over 1 plus x squared dx converges. So this is again something that you know. So ideas that will be useful here, which apparently most of us have forgotten a lot of it. So you can make a fraction bigger by making the denominator smaller, or by making the numerator bigger. 2, whenever you see a trig function somewhere and you want to get an inequality in there, you should always be thinking of things like cosine and sine between -1 and 1. That is going to be very often useful to actually replace a trig function with numbers when you actually have inequalities in place. So that's always something that you're looking for. And to kind of start off with a small inequality that you know, and then build up to a larger inequality. Right? These are all skills that you would have learned when you practice like squeeze theorem and stuff like that from Calc 1. Like you did a lot of this manipulation. So that's probably something that you guys should review from your Calc 1 notes. Squeeze theorem and all that good stuff. Like a lot of the skills that you use there is what you're using here. So if it's kind of hard for you to follow, that's where you're missing. That's where the gap is. So let's continue. Let's soldier through. Ideas? What do we do with this one? Yeah?
Compared to 1 over x.
Compared to 1 over x.
Yeah, because isn't it where on the integral of 1 to infinity, 1 over x, that diverges because p is,
Sure, how would this compare to 1 over x though? Is 1 over x larger or smaller than 1 plus sine squared over radical x? Like, how do you make a comparison here?
would be smaller.
How do you know?
The power, because it's a radical x, which is a half, and then the 1 over x is just the power of 1.
Okay. So what does that mean?
They both diverge.
No, like, so you said, okay, if you have 1 over x as a half, that's a smaller power, and if you compare that to 1 over x has the larger power of the x integral. What does that mean for those two integrals? Like, ultimately, I want to know if it's larger or smaller than this. Yeah.
Could you use like 1 over rad x instead?
1 over rad x is a better, that's why I'm kind of wondering why your brain jumped to 1 over x. It seems farther away from this than we need to get, you know what I mean? So 1 over x is indeed smaller, but now you have to really justify why it's smaller. Also, you're kind of getting lucky for the fact that it starts at 1, because if I started at 0, then it's no longer true that 1 over radical x is always larger than 1 over x. Because between 0 and 1 it's going to behave differently than between 1 and larger. So 1 over x is just, it's too far removed. Get something closer. 1 over radical x. Why not use the radical? We have theorems that will cover that case. That being said, why didn't I compare this to 2 over radical x? Right? In the last problem, we replaced the cosine squared with 1, right? Why didn't I do that here? Why do you compare it to 1 over radical x as opposed to 2 over radical x? Yeah.
Is it because you could take out the 2? Like, you could take out the 2 out of the 2 over rad x, and then it would be a little harder to compare.
Well, if there's a 2 in the top, it's not going to be harder to compare. Because essentially, if we're comparing this to, so you want to compare it to this integral. But what about this integral? Like, why wouldn't this be the one that you compare to?
I mean, you could use that. Like, you could use the 1 over rad x, and like, if that diverges, then that means the first one diverges. But if you use the second one.
Oh, well, what about both of these? Do these diverge or converge?
Diverge.
They both diverge. Okay. Why would someone pick this one as opposed to that one?
That one's larger than
Because this one is larger than the original. Okay? So if you look at 1 plus sine squared x, right? the biggest sine squared can be is 1, which means if I replace that with a 1, I get something larger, so that's this guy, right? The smallest that could be is 0, so if I replace the sine squared with a 0, I would get this guy. So they're very similar in terms of convergence or divergence, but in terms of inequalities, they're very different. Now, the follow-up question is, knowing that these two are different, why would I pick this one as opposed to that one? Or should I pick this one? Maybe that one's better.
Because if you know that diverges, then that means the middle one also diverges as well.
Right, because if this one, well, we know that if I throw an integral on top of that, this diverges. But if the bigger one diverges, what does that tell us? Nothing, right? Which means, if you think, oh, every time I see a sine, I'm just going to sine squared, I'm just going to replace it with a 1, you're going to get in trouble, because this is going to diverge and give you nothing. Conversely, this one also diverges, but it's smaller. So when this guy diverges off to infinity, it's going to force that guy to diverge off to infinity. So this is actually the better one to compare it to. They're very similar, but it's important that you know how to choose properly. You're choosing based on inequalities. And of course, again, all of these are greater than or equal to 0. So here's how something like this would go. So again, you kind of start the same way. Start with the trig function, kind of build things up. You know that your sine squared x is between 0 and 1. This would mean that your 1 plus sine squared x is between 0 and 2. This would mean I can divide everyone by a radical x, which is going to be me dividing by some positive number, which is this. Now at some point I know I'm going to want to take integrals and then talk about convergence. And I also know that theorem 1 over x to the p diverges if my p is smaller than 1. So it automatically means I would choose to ignore this side and continue the problem with the other side. And so with that, I would follow up with now we have 0 is less than or equal to 1 over radical x is less than or equal to 1 plus sine squared over radical x. So 1 plus 1, 2. And this guy diverges. Since our p is less than 1, our p is in fact a half. So this means that this guy also diverges by direct comparison. The idea, of course, being just because you can compare it to something doesn't mean it should. Your comparison has to behave with inequalities a certain way, which means you need to find something larger that converges or something smaller that diverges. Just because you can put something between inequalities doesn't mean that as they present themselves is how you should take them. Right? And again, exactly the same trick that you would do if you imagine this was a squeeze theorem problem. Start out with a trig function, build up to the original function, see how the inequalities are showing, and then pick which inequality is convenient for the problem that you're looking at. I want to show convergence, so I'm going to pick this one. Showing divergence is not going to work. I want to show divergence, so I need to pick the lower one that diverges, not the larger one that diverges. So that's how that one would go. What about the next one, D? Ideas. I think that was on the quiz. I think I put that on the quiz. We did this one converged. this one diverged. Now we're up to here. Is it gonna converge or diverge? What do you guys think? What did you try? What did you put?
This is Dr.
Okay, what's your justification?
Because the power underneath is x to the 3 over 2.
Okay.
And because we know that 1 over radical x, I mean, sorry, 1 over x is 1, and we know that diverges.
So coming in?
So since that's smaller, that, we know that,
This is smaller than what?
no, the 1 over x. Small.
1 over x to the 3 over 2 is smaller? Are you sure?
No, just 1 over x.
1 over x is smaller than this.
Correct, yeah.
How do you know? And again, you're going really far away. Why not compare to 1 over x to the 3 over 2 as opposed to 1 over x? Why do you go for 1 over x? Wouldn't that be nicer?
Yeah.
I mean, it's closer. You know what I mean? Do you know about this guy? Converge or diverge? Does this converge or diverge? Hmm?
The converge, wouldn't it?
It diverges?
Converge.
Yeah?
Yeah.
It diverges. What are you guys missing?
Oh, it's not starting.
Isn't that so confusing? Like, you made it sound like it was going to converge. I'm like,
Attention to details.
this is what I did, it diverged.
1 over x to the p theorem works for 1 to infinity. Right? So this converges if your p is larger than 1. This does not apply to that. Okay? So you shouldn't be thinking about that at all. It's not the same scenario. How do I know that this diverges? Why does that matter?
Because if it's less than 1, then it converges.
How do you know?
So if you're from interval from 0 to 1, it diverges if it's greater than or equal to 1.
That might be a theorem, but I didn't tell you about that theorem. That wasn't a theorem I gave you.
It's because like zero's like the bad point for that.
Yeah.
So once you like find the limit and do all that, you end up with like an infinity somewhere.
Yeah, I mean,
Yeah.
the power rule is the answer.
Yeah,
It's basically
well,
the power rule.
yeah.
This is like an x to the minus 3 over 2. Alright, I'm going to integrate that, the power is going to stay negative. Right, so I'm going to end up dividing by 0 when I try to take the limit approaching 0. So the power rule is really how I would know this. So this diverges considering the power rule. So be careful, attention to details. Limits do not match up with the theorem that I gave you. Okay, so if that diverges, how is that going to be useful to me here? I would need this to be smaller than that one. And in fact, I do have that. This is definitely positive on that. Now the question is this true? Yeah?
I would say yes,
Why?
because I thought of secant squared as like 1 over cosine squared,
Okay.
and then cosine squared could be 0 to 1. So it's going to be either 1 or greater than 1.
Right, so if we were looking at, say, y equals cosine, or I guess you can think of it as cosine squared. So cosine squared is going to look like what? It's like this, right?
Yeah.
And we have problems when that guy hits 0, right? Because our secant is 1 over cosine. So when we hit 0, that creates asymptotes for the secant, right? Now when your cosine hits 1, what happens to the secant? Well, it also hits 1, right? So the secant passes through these coordinates here. It passes through the peaks. Now the question is, what happens away from the peaks? Well, if I move to the left or to the right, I am now dividing by a number that's closer to 0. The fraction is going to get bigger, right? So the secant squared, those guys are going to shoot up asymptotically to those guys. So that implies that my secant squared is actually larger than or equal to 1, which means this actually holds. This is actually, it's true that this is larger. And so now, this means that this guy 1 diverges by direct comparison to this guy. So as you're noticing with these, it's a different kind of skill somewhat. It's not just straight up, I'm awesome at integrals, so I'm going to be awesome at improper integrals. It's kind of a different ballgame, especially when you're using the comparison theorems. So comparison theorems now just, it's testing your function sense. Do I know what's bigger than what? Do I know how to create something that's bigger in some easily predictable way, right? So don't just jump to like a 1 over x. 1 over 3, 1 over x to the 3 over 2 is a better thing to jump to. And it's something that you'd be able to compare relatively easy. So you need to know how to compare things to each other. Now, problem E, just a fair warning here, is not going to be that receptive to what we've been doing this whole time. But this kind of skill, it's very important that you build it up. Problem E is going to throw all that in the water though. So maybe you can start with problem E on what you'd be thinking about, and then we'll see what issues arise. So if I'm looking at from 1 to infinity, first, what would you guess? Converters or divergers? That's also another thing you should be saying. It's like if you're totally lost, you should at least know how to guess in the right way. I'm guessing this is going to converge. Or I'm guessing this is going to diverge. Like, what would you guess if you had to guess?
Diverge.
You would guess diverge? Why? What's your reason?
The denominator's power is greater than the numerator, so if you thought about it in terms of infinity, just get infinitely smaller. I'm probably wrong, but that's what
So you get converts, totally the opposite.
Yeah.
Are you just trying to be confrontational?
No.
It's just like, you know what, I'm going to disagree with it.
Because if you were to, I mean, I don't know, if you could multiply all of them by 1 over x, then you could simplify the whole fraction. And then you would see that on the interval from 1 to infinity, the power on the bottom is greater than 1. So then it would converge.
Why did you divide by 1 or multiply by 1 over x?
Just a simple, I don't know, it was simplified.
The 1 over p, I think, applies to that.
Yeah, the 1 over.
Huh?
I think it does converge.
Can we kind of simplify it to like we're just focus on the bigger term, so you have like x cubed over x to the 5th, and then that just simplifies down to 1.
Right,
over
that's
x
a
squared.
nicer way to do it.
Oh, and then apply the 1 over xp thing.
You're right, you're right.
You were kind of getting towards that, but again, you're going with that 1 over x thing. 1 over x cubed would have shown you that a little bit nicer. So now you didn't go big enough. Right, we're going off to infinity, and we should know when it comes to infinities, x cubes versus x, no comparison. These guys almost don't even matter. They might as well not even be around. Same thing with these guys over here. They might not even matter. So I look at that and I'm like, random guess. Ignore all the little guys. The big guys are going to control things more. So now if I just focus on those guys, I'm like, that kind of looks like a 1 over x squared. Then I have this theorem from 1 to infinity of 1 over x squared that converges. So my guess would be convergence, right? So now, if I guess converge, now I have a goal. I need to find something larger that converges. So now what? Now here's what we'd love to do. We'd love to actually just do what we just did and ignore all the little guys, right?
Yeah.
Just forget about these guys. Like, why are we worried about them? Okay, so if I forget about those and I talk about this guy, just the x cubed over the x to the 5th, how does this compare to that? How would this one compare to that? Whereas this one is actually equal to 1 to the infinity of 1 over x squared. Bigger or smaller?
Yeah, that's what you were trying to do. Oh, yeah.
Bigger or smaller? What are you guessing? We'd love for it to be bigger.
Yeah.
But is it bigger or smaller? I feel like it'll be smaller.
I feel like it'll be bigger.
Why? I mean, I subtracted something in the numerator, which makes it smaller.
Okay.
But then I also subtract something in the denominator, which makes it bigger.
Yeah.
So this change that I would love to make, it makes it bigger and smaller at the same time.
So what you could do is you could make, like, you could see if 2x plus 1 is greater than x plus 10. And then if it is, then that's bigger.
Is that true? Is that a mathematical fact?
No, because like if the 2x plus 1 is bigger than the x plus 10, then that shows that you subtracted more from the denominator, which makes the whole thing bigger.
Is that true though? Like as long as, if I have a random fraction
Yeah.
and I subtract a little bit from the numerator but I subtract a lot from the denominator, is it automatically bigger? Seems that's an assumption you're making.
Probably.
Can you tell me about a theorem that says that?
Oh.
I don't remember a theorem that says that, so I'm not gonna. I don't know the answer to that question.
I thought that was an answer.
But that should kind of tell you what's going on here. You don't need to know. So the thing is here, shrug. No idea. Right? So now the question is, what do we do? So there was a guy that I spoke about last time, who we've all but ignored in today's class. And he didn't actually care about inequalities. Do you remember that guy? The limit comparison theorem.
Oh yeah.
Right?
Yeah, I remember.
So I got you guys used to thinking about direct comparison, but remember there's something called limit comparison. Now, what was special about the limit comparison? it compared f and g. So it said, you know, if you notice that the limit of f of x over g of x equals L, and your L is positive, then this guy, assuming that we actually can compute them, and this guy will both converge or both diverge. Now, the important thing about this theorem is that notice it doesn't actually say anything about who's bigger or smaller here. Right? They don't tell me, oh, this has to be bigger than that, or this has to be smaller than that, and they both have to be greater than 0, or whatever is going on. Non-issue. If this limit works out, they do the same thing. So, if you're in a situation where the obvious thing to do would be to ignore certain terms, but you don't know how that affects an inequality, use the limit comparison instead of the direct comparison. So maybe I should write that in a note. So here's where the limit comparison comes in handy. With all the problems before, we could know for sure who's bigger or who's smaller, or you should know for sure. I don't know if everyone in here could realize, oh, secant squared is always bigger than 1. Like things like that, you're kind of expected to know. But, so before this problem, everything that I compared it to, I could always know, well, yeah, this is bigger and it converges, or that's smaller and it diverges. In this situation, not clear. So, something you should notice, limit comparison is convenient. When we want to compare things. But don't have all the inequality data. So I want to do a comparison test, but I don't know who's bigger or who's smaller. Limit comparison. So that being said, let's actually apply the limit comparison. So I know when I'm going off to infinity, the smaller guys don't matter, so I ignore them. But I don't know if I got something bigger or smaller, so what I'm going to do is instead of directly comparing these two, I'm going to limit compare these two. So I'm going to set my f of x equals the x cubed plus x plus 10 over x to the fifth plus 2x plus 1, and the g equals 1 over x squared. Then, if I look at the limit as x approaches infinity of f of x over g of x, what is that going to look like? Well, that is going to look like, take this divided by that, it's going to flip and multiply. Limit. So I can multiply this out. This is x to the fifth plus x to the cubed plus 10x squared over x to the fifth plus 2x plus 1. What's that limit?
1.
It's 1. How do you know?
Powers are the same, the highest powers.
Highest powers are the same. Ratio of leading coefficients. Again, something from Calc 1. You have to remember everything from Calc 1, basically. So, pretty much the only thing you don't have to remember from Calc 1 is the application stuff, really. So, if you forgot about related rates, you'll be fine. Or like optimization, you'll be fine. You might need it later on, but in Calc 2 you're not going to need it. Like all your derivative rules, all your limit rules, all your integration rules from Calc 1, you need to remember them all. All your inequalities, squeeze theorem, L'Hopital's rule, all of that. One rule that you know is that limits at infinity of rational functions have 3 cases. You'll get 0 if the highest power is on the denominator. You will get the ratio of leading coefficients if the highest power is the same on the top and bottom. And if the highest power is the larger on top, you'll get plus or minus infinity depending on the signs of the things here. In this situation, we get 1, which happens to be positive. So it's a positive real number. What does that tell us? This means both this is 1 to infinity of f, and 1 to infinity of g. Both of them do what? Converge. They will both do the same thing, is the idea. And for g, I in fact know how it behaves because I have a theorem that tells me. So I know this guy converges, that guy also have to converge. And again, I don't know who's bigger or who's smaller, but for the limit comparison test, I don't need to know. So this guy actually converges. So this guy converges is the upside. So I think that was a nice mix of problems here. A lot of nuances, I think. I think we probably went through all the nuances that we're going to get through here. So certain things for the direct comparison theorem, things you want to note. You need 0 less than or equal to f, less than or equal to g. It's important that you remember the 0. Then if your g converges, your f is going to converge, and if your f diverges, your g is going to diverge. So you have to make sure that the inequalities line up in the right way. To accomplish this, things that you can do: make the numerator smaller, or make the numerator larger, or the denominator smaller to get something bigger. If you have trig functions, try to replace them with constants by knowing how trig functions behave. Start out with a trig function, get its limits, build up to the bigger function, and then you can kind of see where the inequalities will fall. Other things that will be useful is just, if you're especially going off to infinity, ignore all the little guys. They're going to matter less and less, and compare to what's left over. If it's not clear who's bigger because of the kind of manipulations you did, sometimes it'll actually be quite clear who's actually bigger. Like if this was minus and minus, then it's actually clear that that guy's bigger. But with the plus and plus, not clear at all. If by doing manipulations you are not sure if what you got is bigger or smaller, use limit comparison instead. Right? So in fact, on all the previous problems where we compared like 1 over x radical x, blah blah blah, all that good stuff. If you weren't sure who was bigger or smaller in the previous examples, you could have done the limit comparison test to actually determine what's going on. But yeah, that's that. And that's the last thing with improper integrals. So sometimes you compute them directly, we can actually find the area under the curves. Sometimes though, we can't actually compute the integrals directly, or it's going to be very, very annoying. So we just use comparison theorems. I can compare it to this and I can know it's going to converge or diverge, even though I might not know what it will converge or diverge to. And any general questions on this so far? So that idea kind of leads nicely to the next topic, which is approximate integrals. So suppose I know an integral will converge, or an integral, it doesn't have to be improper. An integral is going to give me an answer, but I don't know how to actually get to that answer. What are my options? Right? Let's say none of our integral techniques will work out on something. So in the next section, we're going to learn how to approximate definite integrals. So, I forgot what section, 11.7. Don't quote me on that, I don't remember the sections. Okay, so it's called approximate integration.
I think it's 8.7.
Yeah, it's 8.7.
8.7. Am I in the I know in the previous calculus book, I think it was in chapter 11. Something else you might hear them call this, aka numerical integration. So this is the idea here is given some definite integral whose value is difficult to compute via the fundamental theorem of calculus. Not that it's impossible, not that it's improper, it's just a very hard integral. So for example, integral of 1 up to 5 of e to the x squared dx, right? It's not improper, but at the same time, pretty much impossible for me to do that. I do not know the antiderivative of e to the x squared. It doesn't have one, right? But how would what if I wanted to know what is the area under the curve for that function, right? So very difficult to compute. In fact, this one's going to be impossible to compute. So given some definite integral, the value is actually difficult to compute using the fundamental theorem of calculus. We want to go about approximating what the answer would look like. Now, a lot of the groundwork here was also laid in Calc 1. You actually did a section like this in Calc 1 when you were talking about Riemann sums and you did left-hand rule and right-hand rule and midpoint rule. Those things are still going to be true. It's just that the text now at this point, those guys are too easy. You want some more sophisticated methods. So we saw these in Calc 1. Yes.
Isn't the three, rules for numerical integration, one of them is the midpoint rule, and the other one is the trapezoid rule?
We saw this at these in Calc 1, namely midpoint rule. So that was one of the ones you could have listed on the quiz, one of the approximation techniques. There was also the right-hand rule. There's also the left-hand rule. And in these, the idea was that some function f of x, and you want to approximate the area between a and b. The idea was you dissected this into subintervals. The length of each subinterval was delta x. And you pretty much erected rectangles on each subinterval. And you chose the rectangles in a very special way. With the midpoint rule, you let the middle of the interval touch this, and that's the height. With the left-hand rule, the left side touched it, and that's the height. With the right-hand rule, the right side touched it, and that was the height. Right? But you came up with a method for creating rectangles under the curve, right? By one of these rules. And our x was often called x0, our b was called xn, and then we label all the other xi's x1, x2, x3, so on and so forth, right? So we set those up, and we could actually compute the area was the sum, or was approximated by the sum of f of xi times delta x, where our I goes from, where our I depends on the method.
Smith, according to the internet, one of the techniques for, numerical integration, isn't one of them like trapezoid, technique rules or trapezoid rule?
Yes, I'm currently talking about the ones that were covered in Calc 1. Right? There are some conceptual things I want to remind you guys of. I'm not going into it as deeply as I did in Calc 1. If you're completely clueless on this stuff, you definitely need to watch the Calc 1 videos that I have on this. But I just wanted to remind you of how these things were built up. You had some function, you dissected it, the length of each interval was delta x, and you pretty much set this guy up. And the i's you chose depended on the method. So for a right-hand rule, you would choose, I would go from 1 up to n of your f of xi delta x. And for the left-hand rule, your I would go from 0 up to n minus 1 of f of xi delta x. And for the midpoint rule, you choose something entirely different. It was from 1 up to n of f of xi star delta x, where your xi stars were the midpoints. So you create the summation, you add up all the length times height of the rectangles, and use that as an approximation. And of course the idea was to make the approximation better, use more rectangles, increase the number of n. And in fact, when we let n go off to infinity, that's what an integral is. That created the definite integral. The definite integral is in fact the limit as n approaches infinity of this expression, right? That's how you created this guy, right? So now we want to expand that idea a little bit. I know I also asked this on the quiz. What is delta x? How do you find it?
B minus
B minus a over n. So that was the answer to that. Right? Take the length of the interval, divide it into n equal sections. So the length of a horizontal length is the right minus the left. Right? So if this went from 1 to 5, what is the length? 5 minus 1 has length 4. Right? So you take b minus a divided by n, and that was the length of each subinterval. Okay. Now, moving on. We're going to expand. Because, yeah, rectangles were so last semester. We're done with rectangles. Rectangles are deemed not to be as efficient. So we have, let's say I have a curve like that. Curve like that. I'm just redrawing the same curve. So this was not meant to be comprehensive at all. Just wanted to jog your memory slightly so that when I start explaining things here, it's not going to totally go over your heads. So you set up the left-hand rule, right-hand rule, midpoint rule back in Calc 1. We're going to expand on that here. So ultimately, by the end of this class, there are 5 complete methods that you should know. So on the quiz, I asked you to tell me about 3 of them, but ultimately there are 5 of them. So let's say I wanted to find the area from A to B here. And if I were doing, say, the left-hand rule, let's say I dissected this into 4. So there are 4 subintervals. What I would do is, on each subinterval, I take the left side, create the height, left side creates the height, and move over. Left side creates the height, left side creates the height. That's what the left-hand approximation gives us. Some overestimation over here, an underestimation over there, but that's what the left-hand rule is actually going to look like. If I went to the right-hand rule, same idea, A, B. But in the right-hand rule, we instead take the right side of each subinterval, create the height. The right side of the subinterval creates the height. The right side of the subinterval creates the height. Right side of the subinterval creates the height. So you can add up those areas of those 4 rectangles, and that's the right-hand approximation for the area under the curve. We also had the midpoint. So I wanted to do something from A to B, dissect it into 4, just like that, like that, like that. And instead of the left or the right, you took the middle of the interval. That creates the height. So the nice thing about this one is it kind of gives a little bit of underestimate while at the same time giving an overestimate, kind of balances things out. Whereas with the left or the right, most of the time they give either a complete overestimate or a complete underestimate. And depending on how the curve shapes, they might give you a little bit of both. But the midpoint was meant to kind of balance things out. And you take the middle of the interval, and that creates the height. The middle of the interval, that creates the height. So that's what the midpoint would be. And so you'll multiply delta x by this point, that point, that point, that point. When you plug into the function, that creates the approximation. Same thing here, same thing here. Now, we're going to new and improved. New. there is something called the trapezoid rule, as Jason mentioned. So, what's the idea behind the trapezoid rule? Well, use trapezoids. Instead of using rectangles, what we're going to do is we're going to use trapezoids to approximate what's under the curve. Why? Because it might be nicer. The idea is going to be on each subinterval, let each endpoint touch the curve and then connect those with a straight line. The idea being that if you see over here with a rectangle going straight horizontally across, it misses a lot of stuff here. However, if I made the line angled that connects these two dots, it misses less stuff. That's kind of the idea behind it. Same thing over here, connect these two dots and create an angled line going there. Same thing here, create these two dots, create an angled line going here. Here, create these two dots, create an angled line going here. And the idea is this guy will hopefully be a better approximation than all of those guys combined. Because whereas these guys have to go to horizontal, if my thing is curving a lot, they're going to miss a lot of stuff. They're going to be overestimating, underestimating, not going to be very close. Whereas this one, the idea is it's going to be closer than just a straight horizontal path across would be. You would actually be able to approximate the curve better with fewer rectangles, is the idea. And I'll talk about why that would be important pretty soon. Because you might say, well, I mean, how much better this can be? Well, if you're using a computer to do this, remember, you're doing like thousands, millions of little dissections here. And the idea is, if you can have a computer do 1 million dissections as opposed to 2 billion, it makes a lot of difference, right? So the fact that you can get closer with less stuff, it's, you know, by hand you're not going to notice the difference, but a computer will actually notice the difference. You do want to cut down on computation times in general. Now, in this, there's another new technique that we're going to look at. Do we know what the last one is? Simpsons. So for that question we're asked, name 3 approximate integration techniques. You could list any 3 of these names, and that would be the point here. What Simpson's rule does is the following. It says, forget all your straight line angled stuff, we can do better. Let's actually approximate these with curves. They're curvy, let's use curves to approximate them. So what it does is it takes 2 subintervals at a time. It will take the 3 endpoints of those subintervals, and what it does is it creates a parabola that goes through all 3 points. Then it goes over here, creates those 3, and then it creates a parabola that's going to pass through those 3 points. And then basically, it actually approximates the area under the parabola. And the idea is, a curved line is going to fit the curve even better than a straight angled line would. So we kind of build up to getting better and better and better. Yeah, the left and right hand had their problems, too much over and underestimation. We tried the midpoint rule to kind of overestimate and underestimate at the same time, kind of balance things out. But ultimately, wouldn't it be nicer if we could get closer to the curve? So let's actually connect them with angled lines. That gives you the trapezoid rule. If I try to connect the curves with other curves, specifically parabolas, you get Simpson's rule. So these are the 2 guys that we're going to worry about now. So what would a formula be for that guy is the question. What would a formula be for both of these? We already know the formulas for these from Calc 1. So that these one at a time, trapezoid rule. Do you remember the area of a trapezoid? So if you have, this was height 1, this is height 2, and this here is the length between them. I don't know what you want to call it, x. What is the area here? 1/2?
mean, y1 plus y2
times x. Exactly. So if I have a function like this, so let's say this here is x0, x1, x2, x3, x4. The y value here is y1, y2, y3, y4. I'm sorry. 0, 1, 2, 3. So those are the heights. The area of this part, this first one, by that formula, well, it's going to be 1/2 times the y0 plus the y1 times the distance between them, which is delta x. Same thing here. This is going to be 1/2 times y1 plus y2 times delta x. This one here is going to be 1/2 times y2 plus y3 times delta x. This one here is going to be 1/2 times y3 plus y4 times delta x. What you're going to notice now is that 1/2 delta x is actually a common term. So if the area is just the sum of these areas, and you would notice that my delta x over 2 is a common term. If I factor that out, what would I be left over with inside? Notice that I have a y0, that's my f of x0. But notice how y1 shows up twice. I would have two y1s. So it's 2 times f of x1 plus there are two y2s. 2 times f of x2 plus dot dot dot. Notice that we're going to have 2's of everybody in the middle, except for the final guy, the y4. That's the only y4 that's there. So it multiplies everyone by 2 in the middle. 2 f of xn minus 1 plus the last one is just f of xn. And that's the trapezoid approximation. We call this t sub n. This is approximating with trapezoids with n subintervals. Pretty much the first and the last y value just stay as is. All intermediate y values, multiply them by 2, double up. You have to actually multiply by delta x over 2 as opposed to just delta x. That's the trapezoid rule. And in fact, you have handouts with this rule. So you'll notice what I just derived was the guy on page 1, this guy right here. So that's the formula that you'll see in your textbook, and I just told you where it came from. Let me tell you about Simpson's rule, and then we get out of here. Next time we're going to do the examples that's on that page. For Simpsons, we need to know how to find the area under a parabola. So we're going to find the area under a generic parabola. So let's say I have some parabola balanced on an interval, passes through these 3 points. Call this y0 is going to be the height here, y1 is the height here, y2 is the height here. This is x0, this is x1, this is x2. I'm going to call the distance here h because I can't bother writing down delta x all the time. Right? How do I find the area under this curve? So the idea is set the parabola to be, let's call it ax squared plus bx plus c. How do I find the area under a curve? Well, we do it with an integral. That's how we do it. So the area is going to be the integral from minus h to h of ax squared plus bx plus c. I'm going to integrate that. That's ax cubed over 3 plus bx squared over 2 plus cx between minus h and h. And plugging that in, that's going to be ah cubed over 3 plus bh squared over 2 plus ch. Now when I go back and plug in minus h's and apply the negative, this one's going to double up, that one's going to cancel out, and this one's going to double up. So I'm going to have that. That expression is going to give us the area. Now, let's make sense of this expression. Going back to my problem, notice that P of 0 is actually just C, which is actually y1. So my C equals y1 in this expression. If I look at P of h, that is ah squared plus bh plus c. If I look at P of minus h, that is ah squared minus bh plus c. You can notice that this is y0, while that one is y2. And I can add these two together, right? I would get 2ah squared plus 2c is equal to y0 plus y2. And so now, if I go back here, I'm going to factor out an h over 3. I'm going to have a 2ah squared plus 6c. Notice here I'm going to have an h over 3. This is 2ah squared plus 2c plus 4c. And now I'm going to apply everything I just did over here. This guy, the 2ah squared plus 2c, is actually just y0 plus y2. And the 4c, well, that's just 4 times y1. And so the area under this, if I want to make it equivalent to our old notation, is going to be delta x over 3 times f of x0 plus 4 times f of x1 plus f of x2. Now if I add a bunch of these side by side, what you're going to notice is these guys are going to start doubling up. I'm going to get this alternating of 4s and 2s, starting with the 4. And that gives this formula, right? So that's where that formula comes up. So this guy's delta x over 3. The first y value, then 4 times the second, then 2 times the third, then 4 times the fourth, and so on. 4s and 2s alternate until you get to the last guy, it doesn't. Yeah, that's where these formulas come from. So next time we're actually going to apply them to the problems on the back, but I guess you can try them out before we actually do them. But yeah, that's where they came from, in case you're we'll pick up with that on Thursday. So be sure to carry this with you.
Isn't it supposed to be from Simpson, supposed to be 4, 2, 4, 2, 4,